I have not erased that. Yeah, so in mutation we understood uniform, non-uniform. Uniform just means within the lower limit and upper limit we choose a random value. Non-uniform means when we choose a random value, there are certain values that are chosen with a higher probability, and that probability is determined by the standard deviation. Now the standard deviation can be user inputted or be evaluated on the data itself. When it's evaluated on the genetic material itself, then it's called self-adaptive mutation. To evaluate them, the self-adaptive mutation, we have direct and indirect. Direct meaning we directly apply the fitness function and see which offspring is performing better, and indirect is when we evaluate in comparison to the parent. That is all about mutation. The second thing about mutation is whether or not we are applying the values similarly to all dimensions of the genetic material, or if we are applying the values differently to every dimension, if you're treating every dimension in the same way or in a different way. The robot example, I think, explains it really well. Now this is all about just mutation. Now we come to recombination. I have a very good picture in my head about how recombination takes place, but that is mostly because of binary encoding. So if we take a recombination along this axis, we can simply do 1 1. This part goes here, since you've taken this part here, 1 1 0, and this part goes here, 1 0, and this part goes here, 0 0 0. Like this is simply a crossover. You can apply this crossover to decimal values also, like floating point values also. So 60.6 or 55.5 and 59.2, 59.25 or something like that, and then you take 75.3, 66.2, 74.8, and now you can take a crossover about any axis, let's say this axis, and you say 60.6, 55.5, 74.8, 75.3, 66.2, and this part here, 59.25, since we took this part here, right? These are the two offsprings created by the crossover of these two parents. This is very similar to how binary encoding of recombination takes place, and this is simply called discrete recombination. Like I said, it's just the same as how we've done it in binary. Now that we have now that we have some values that have a value, like 0 and 1 only show you a type of set if it's on or it's off, but there's obviously a difference between 2 and 3, and it could be possible that 3 has a higher impact than 2, right? We can take recombination of 3, 4 and 5 and 6, 7 and 8, and what we can do is we can just average all of them, right? 9 by 2, 11 by 2, and 13 by 2, 4.5, 5.5, 6.5. This could also be an offspring of them, right? Arithmetic crossover of two genes can also take place. Now how this arithmetic crossover takes place also comes in two types, right? Single arithmetic recombination or whole arithmetic recombination. In single arithmetic operation, what we do is we choose a position and we only take the average, or we only take the weighted average of that position. Let's say we have 1 2 3 4, I'm just writing this example here, 4 3 2 1, and we choose position k is equals to 2. Now for this position, alpha is equals to 4. Now the concept of alpha here means which parent is given what weightage, right? In 0.5 weightage, both of the parents will have equal weightage and it will simply become the average. But if we have 0.4, the two offsprings of these two genes can be 1 2 into 0.4 plus 3 into 0.6, which is just 1 minus 0.4, 3 4 4, 2 into 0.6 plus 2 into 0.4. Like this time I took 2 into 0.6, first time I took 2 into 0.4, and this will be 2 1, right? These can be two offsprings that are created, and that's why it's called single arithmetic. That means we only apply this type of crossover at a single position that we choose randomly, and we apply it with a certain weight, which called as alpha. The other type of arithmetic operation being a whole arithmetic recombination, which is, like I said earlier, we just do like an average. For example, 1 2 3 4, 4 3 2, 1. And if our alpha was 0.5, we would just take the average as 5 by 2, 5 by 2, 5 by 2, 5 by 2, all parts being 2.5. Now if we take our alpha as 0.1, what we can do is 1 into and take this parent to be the lesser dominant. This parent will have 0.9 contribution, this parent will have 0.1 contribution. So this will be 3.6 plus 0.01, 0.27 plus 0.02, 0.18 plus 0.03. Like these are all different dimensions. 1 into 0.9 plus 4 into 0.1, and you can calculate accordingly. And for the second offspring, we will take this as 0.9 and this as 0.1. So I hope you're able to understand the two types of arithmetic recombination we can do. Single, applying it at just one position. Whole, applying it at all positions. Now blend recombination is, okay, when we do this type of arithmetic, and since we are taking the weighted values, it means these values, the new values, will always lie in between the two parents, right? Our first gene is 1, 2, 3, 4, 1, 2, 4, 3. Next gene is 4, 3, 2, 1. Now the new offspring value created here will always be restricted between 1 and 4. There is no way that it can escape between, can be 0 or can be 4.5 or can be 5.6 or something like that. This type of arithmetic constricts it between the offspring at that position will always be in the range of its parents. For the blended recombination, there is some sort of maths we do where it is possible to take the value outside of this range itself. Now, I don't know how that mathematics is done, and I'm not going to bang my head over it. I'm not even sure how it's written in the book, but I think just understanding this much is enough. Like for recombination, there are 3 types. Either we combine it like we do with binary, where we just take some positions from here, some positions from here, cross over and get 2 new offsprings. Then we can do arithmetic, where we arithmetic of 2 types. The first type being we choose a random position and take the weighted average there, or we, instead of choosing a position, we apply the weighted average to the entirety of both 2 genes. The blend recombination is an extension of the intermediate or arithmetic recombination, since the offsprings of the 2 parents and at each position of the offspring will always lie in the range of the parent's position, parents at that position. Therefore, blend recombination does some magic maths where it allows the new offspring value to be beyond the range of the parents. I think studying this chapter in this much detail is more than enough. I would just advise you guys, since I know I talk very fast, just pause at every sentence I'm saying and try to read the notes side by side. I'm sure you will be able to understand. Try not to message me personally, just at me on the group and ask, and I will probably clarify anything that I've said that is slightly confusing or not.